In this video, we want to talk about the compound lenses. What is the focal points of the two lenses that are close together or they're at the distance d from each other? So let's say we have two lenses, f1, f2, at distance d. Now we want to find an equation for a representative lens that we call it f for these two lenses. Actually, we want to prove that equation. We know what is the equation, but right now in this video I want to show you a simple way to prove it for yourself. So at first, like all other optical systems, usually when we have two lenses or three lenses or a lot of lenses in uh, one after each other, we usually use this technique. So you start from an object at infinity, or it can be any object at any place. So the image from the first lens, the image of the object at infinity from the first lens is gonna act like another object for the second lens. And then that object makes an image. Then, if you have a third lens, you can use this process to find the last image. There's gonna be the image of your total for the whole system. So right now, let's consider we don't have f2. That's the first step. We don't have any f2. So we only have f1, a beam from infinity at the height of h1 goes to lens f1, and because that's the definition of the focal points, when the beam from infinity or parallel to the optical axis hits the surface of the lens, then when the beam hits the optical axis, the distance is going to be the focal length. So we have lens 1, and that's the focal distance. So this beam goes to the optical axis, and this angle we call it theta delta 1. So right now we have a object for the second lens is actually that's the image of the first lens. So right now we have this object at distance O2, because that's acts like an object for lens 2, and this distance is a positive value, but because it is on the right hand side of the lens f2. And I have another video that the lens convention, where we put positive values, but in a summary, anything is in the right hand side of the lens we consider as negative value, anything on the left hand side we consider as a positive value. So right now, the actual value of O2, because the distance, it cannot be positive or negative. For example, it can be 2 centimeter. So it's a number. But the value itself is negative 1 over 2 centimeter. So we put negative 1 over O2 plus 1 over X. So what is this X? X is the actual final image. So we have an object here and we image it through f2, and the image is going to be here. So that's the image of the combined f1, f2 lenses. So this distance, we call it X. That's actually the back focal length of these two lenses. So as I said, O2 is equal to f1 minus d. So we have O2. Let me actually change it to, so we have O2 equal to f1, which is this distance, minus d, and d is the distance between lens f2, lens f1 and f2. So we put this equation, this simple equation, into this one, and we get to this equation. We have 1 over f2 is equal to, it was f1 minus d, because we have a negative sign here. I change it to 1 over d minus f1 plus 1 over x. So 1 over x is unknown for us now. Now let's think about this value. So right now, when we have two lenses, the representative of these two lenses, that we call it f, it can be somewhere here. But when you have a beam that is you continue from f1, then it's bended and then goes to the focal point. So if we continue this line and that line, then that you can get to the position of f. But this distance is also unknown for us. But we know that this distance is f. which is representative of the distance of lens 1 and lens 2. So as I mentioned before, this angle actually is delta is equal to, because this angle, these two lines are parallel, and we have a line that's passing through these two parallel lines. This angle is delta, is equal to this delta. So delta, tangent of delta, or delta itself, because it's paraxial for small angles, is equal to h2 over x over this distance. So we have h2 over x. At the same time, when we continue this triangle, here this distance is h1, because these two lines are parallel, comes from h1 at here. So at the same time, this is equal to h1 over f, this distance. So now we have a good definition for 1 over x. So 1 over x is equal to h1 over h2 times 1 over f. So right now 1 over x is known, but again, h1 over h2 is unknown for us. So what is h1 over h2? So in order to find h1 over h2, we can actually look at delta 1. So delta 1, this line that comes from infinity and it bended from the first line, and we continue it, that's for, as I mentioned, let's ignore lens 2. So that angle is delta 1. So delta 1 is equal to, from one perspective, that's the focal length of lens 1, which is f1, from here to there. This one is h1, tangent of delta 1 is h1 over f1. That's very well known. And at the same time, we have the same angle here, which is equal to h2. This is the height that we have here. And this distance is f1 minus d. So it's equal to f1 minus d. Then we have a good definition for h1 over h2. So it's equal to f1 over f1 minus d. Now we have everything. We have 1 over x, we have h1 over h2, and then we have 1 over x, and we have the equation as a function of f2, f1, d, and 1 over x that has 1 over f. So we need to solve these three equations together. So 1 over x is equal to h1 over h2 times 1 over f. So we plug h1 over h2 here, we get to this equation. 1 over x is equal to f1 over f1 minus d times 1f. And then 1 over x, we plug it here. So we have 1 over f2 equal to 1 minus d minus f1 times x 1 over x, that we have f1 over f1 minus d times 1 over f. So from this equation, we multiply both sides by f minus d over f1. We multiply both sides of this equation. So then we have f1 minus d over f1 plus f1, because this is cancelled. And then, because this one is d minus f1, this one is f1 minus d, they cancel, and we have a negative sign here. And we have 1 over f here. And now this equation, we just factor f1 from this equation to here. We have 1 minus d over f1 times 1 over f equal to minus 1 over f plus 1f. So 1f remains on this side, 1 over f1 goes to the other side. We have 1 over f equal to 1 over f1 plus 1 over f2 minus d times f1 f2. So that's the proof for the compound lens. Thanks for your attention.